You know, there might not come a good time in today's lecture for me to hit a pretty important point. In 2000 or 2001 or something in that neighborhood, there was a very good movie that won Best Picture called A Beautiful Mind. And it's about John Nash, whom we'll be talking about today. It's a deep dive into a lot of the things that he went through. John Nash suffered from paranoid schizophrenia. He had a lot of trouble for decades. And it really pulls at your heartstrings throughout that entire thing to see such a great mathematician having to go through something like that. But there's one thing it got wrong. The one thing that A Beautiful Mind got wrong was what a Nash equilibrium is. Of all the things to get wrong, it got what Nash equilibrium wrong. It got the subject of today's lecture completely wrong. They could have taken PS 231. They could have called me. They could have called me and said, "Hey, Rob, could you please let us know what the heck we're talking about here?" Now, never mind that I was dropping out of college the first time around that time, and never mind I never heard of game theory. I could have solved all their problems. And so right now, I want you and me to make a pact. If you happen to make any major motion pictures, or even indie films, if you make any movie that involves the definition of a Nash equilibrium and you don't call me, I'm going to be really fucking pissed off at you, okay? Hey everybody, welcome to PS 231. In my mind, all of you just skipped directly to the A block and you just want to get your problem sets done. In my mind, actually, only about half of you watch the movies, which is fine. These are for you, and if you choose not to watch them, that's fine. I don't know about you, but I find that little clappy intro a little bit helpful for me when I'm editing the movie. That gets me in the mood to do some of the editing that I got to do. And I hope that that's something that gets you excited. I hope you're taking the time just to be good to yourself. You know, if you find yourself feeling a little flat, if things like weird intros full of clappy music to the start of your video lectures, if that isn't getting your blood pumping, well, first of all, you just have good taste. But second of all, you know, just make sure that you're taking the time to sleep well, eat well, rest, do whatever it takes for you to feel whole. Here in the middle of the semester, where we're in the core of the class, we're grinding really hard, we're going through the things that you really expect to see in a game theory class, and I'm assuming that we're hitting similar points of your other classes too. So you're really starting to grind pretty hard, and I want to make sure you're taking the time to be good to yourself, because it's really important. Now, part of that is just learning the discipline that it takes to stop doing the things that you do to be good to yourself, right? So if you need video games in order to feel good, it's hard to stop after an hour, but you might have to, just to make sure you're getting all your work done. But regardless, there's a real balance to strike, and it takes a long time to learn it. I haven't learned it yet. But if you can strike that balance, then you'll set yourself up for success, but also for happiness as you achieve that success. And that sounds really nice. I want all of that for all of you. There, I'm done. Actually, I'm not quite done. I always get the feeling that you're not eating as well as I would like you to. In my mind, that manifests itself as you're eating pasta with jarred sauce. I know that pasta is a good cheap dinner when you're an undergrad, and if you're a grad student, that's basically all that you eat. And I don't want you eating the jarred sauces if you don't have to, okay? So listen. Just take it from me. This is as easy as it gets. Zhong. Pause the video and write that down. Because that's the base sauce. You could make pasta and that, and you'd be perfectly happy. But you could also amend this to add a couple of other things and also be perfectly happy. As this sits, it is vegan, right? One nice thing. I don't eat a whole lot of vegan food. But you could change it however you wanted to. But if you can get this really right, then you'll be just fine for pasta night, which I know is just night. All right, that's enough about clappy introductions and pacts about the movie that you're gonna make and pasta sauce recipes. Let's talk about game theory, right? You've never been so excited to talk about game theory in your entire life. And that makes sense because this is the lecture this is the one that you're gonna need. Of all the lectures, and I say this every time, of all the lectures, this is the lecture that if you take a class in game theory, this is the lecture that you need to internalize. Well, I guess last lecture a little bit too. What's a game? And now we're going to talk about how one studies a game, how one analyzes a game, how one gets to the prediction at the end of a game. Last week, all we did was talk about the games, and then I rather melodramatically talked a while about what a story is about and how it ends are two different things. That's great, but the funding agency wants a prediction. They gave you some grant to write down some game, and they don't say to you, hey, thanks for writing down this game, that's it. No, they want to know what your predictions are. They want to know what you have learned from the game. They want to know what your analysis suggests. And up to this point, we haven't talked about that. All we did was talk about the different kind of stories that you can tell with a strategic form game sort of apparatus, where you have a set of players, each equipped with a set of actions, and each equipped with the utility function over the Cartesian product of those actions. God, I hope you're just reciting that to yourself in your sleep. So today is the day that we begin the analysis. Today is the day that we start to think about how to move from a model to a prediction. And by that I mean, we take the set of all possible strategy combinations, right? That we take that Cartesian product of every combination of my choices and your choices, or potentially many people's choices. We take that Cartesian product and hopefully we can whittle it down. Hopefully we can say, well, my prediction is actually that what everybody will choose is blah. In the game of chicken, it could be that your prediction would be something to the effect of, my prediction is they will both swerve. And there you would be endogenizing a rational choice. You would be saying, I can explain the origins of choice in a strategically embedded environment, given the nature of the game called chicken. And the same for Prisoner's Dilemma, blah, blah, blah. But what you need in order to get from game to prediction, is a concept about what it is to be aggregatively rational. What is it for all of our individual level rationality to be aggregated into a game, into something that we could call a steady state? I know it's hard to believe, but I'm making it sound a lot more complicated than it really is. You'll see that the concepts at work are relatively straightforward, relatively intuitive. There's an underlying story as we try to breathe life into our players, right? So up to this point, we haven't really talked about what their motivations are other than their utility functions. We haven't talked about how they will make choices or what will be the outcome in a game. And so that's all that we're going to talk about today. We're going to do a bunch of examples, but really what we want to talk about is how to get from game to prediction through the mechanism called Nash equilibrium. As a historical aside, you might be thinking to yourself, well, Nash equilibrium, as it's named Nash equilibrium, was invented by John Nash. Not so. The concepts that we'll be talking about are much older than John Nash, who published his seminal papers in economics and applied mathematics and game theory in the late 1940s and early 1950s. The concepts we'll be talking about date back at least to the 1830s, when Augustin de Cournot did a study of how firms will choose how much of output to make when they don't want to drive the price down too much by making too much. And so Cournot's model of oligopoly, which we won't touch in this class, but if you take an economic version of the same class, you'll hit it like week one. That set the stage for the concepts we'll be talking about today. What John Nash did was encode it just the right way to establish that if we think about Cournot's concepts properly, we can be sure that this means of analysis that we'll be talking about this week and next is a good method of analysis in the sense that it always generates a prediction. We will never show up to the funding agency empty-handed. So that's all that we're doing today, is taking the stories that we've learned to love so much over the last week and figure out how they end. I know that it's been hard not to turn to the last page real fast, and it's time for us to do that now. So go get yourself some liquids. Go get yourself a storybook. Go get yourself something fluffy to squeeze on as you go. Get yourself into some soft pants, would you? And we'll get to it. In the A block, I just want to describe what Nash equilibrium looks like when we conceptualize it as a steady state. So Nash equilibrium as a steady state is the primary way of thinking about this. This is Cournot's original concept of equilibrium. We'll do chicken as an example. We'll talk our way through the game of chicken and figure out which, if any, of the 4 strategy profiles that are available there we could call a prediction. What are the things that we could rule out? What are the things that we say are possible? Is it possible for us to go to a single unique prediction? That would be perfect, right? It would be nice if every game had a unique steady state, because then we could go out into the world and say, well, I know exactly what will happen. We'll see that we have to have some humility about that. Now, the steady state approach we'll be talking about in the A block is, a little bit more theoretically appealing, but it can be a real pain in the butt to work our way through. So in the B block, I'll introduce the notion of best response correspondences and show you that Nash equilibrium is actually just the intersection of those. This provides us with a faster way to compute Nash equilibria. It's a real pain in the butt to compute Nash equilibria the steady state way, but using best response correspondences, which we'll see have a nice intuitive visualization in the context of 2x2 games, we'll see that it's a lot faster, it's a lot easier, and then you could intuit your way through the steady state story after the fact if you needed to. But if, hypothetically speaking, you were locked in a room for 2 hours and forced to do game theory problems at the end of a semester or something, you probably want to know the faster way, right? As a substantive bonus, I'll spend the B block ruminating a little bit about what countries do. Undersell it. And then in the C block, I want to talk our way through what Nash equilibrium looks like in the context of that campaign model from the C block of last week's lecture. We'll see that a very particular result arises, and it's a very important result that you will see again and again. You may have heard of this result. I'm not going to name it just yet, but you may have heard it when you see it, and if you haven't, that's fine too. You know, I oftentimes say you may have heard this, but if you haven't, that's totally groovy. I only say that so that the people that have heard it have some sense about what to be looking for as we contextualize things. Well, the first time that you hear a concept, it's tempting to think that you know about it. And the fun thing is you get to see the same concept emerge a lot of different ways. It can emerge in informal texts. It can come up in a game theory sort of thing like we're talking about in this class. There's a lot of different ways for the same thing to pop up. And so whenever I signpost something and say you may have seen that, that's just so that people can draw connections between this strange, abstract storytelling class and what they may have seen in other classes. Remarkably enough, though, our lecture about how to end stories has to have a beginning. And so get rid of all this stuff. Just get rid of it. I'm ready. Are you ready? Are you locked in? I'm totally ready. I'm really looking forward to showing you this because a lot of cool things pop up in the study of Nash equilibrium. So let's get started. So here in the A block, I want to talk about Nash equilibrium as a steady state. I know that you take notes. I'm sorry. In my mind, you don't need to take notes, and that just makes me an idiot. So write this down. The whole point of Nash equilibrium as a steady state is that it's a state of affairs where no one player would deviate from the outcome if they had the chance to. So when you think about what it would take for something to be an outcome out in the wild, in order for something to be an outcome out in the wild, it seems to me that if people had a chance to peel off if they wanted to, if we were at some strategy profile, swerve, if we were at some strategy profile where given where we were, somebody would change their mind if they could, well then we're no longer where we were, right? So this sounds pretty vague and cryptic right now, but this is actually what's happening is Nash equilibrium, particularly when interpreted as a steady state, is a necessary condition for seeing a particular outcome out in the wild. Because if we're not at a steady state, somebody can peel off, then somebody will peel off. That's the whole idea. Let me show you what I mean, though, by talking about the game of chicken. Let's just review the underlying story real fast, okay? So remember, in the game of chicken, I'm an angst-ridden adolescent, you're an angst-ridden adolescent, we are two angst-ridden adolescents. And we are trying to prove who's more awesome. Or we're two superpowers trying to prove who's tougher. Actually, I looked it up. In the actual movie, they're not driving toward one another, they're driving toward a cliff. It's the same idea. The thing with driving off a cliff instead of driving toward one another is that when we drive off a cliff, I have to use a different sort of movie thing. And my very favorite thing is to get to do this. So I'm going to keep the fable as it sits if you don't mind. So remember, I'm the row angst-ridden adolescent and you're the column angst-ridden adolescent. And I can either swerve or I can go straight. As we drive toward one another, I can either swerve or go straight. Okay? And you can either swerve or go straight. And remember, in the situation where we both go straight, that's one happiness point for me and one happiness point for you. Neither of us is the chicken. Neither of us is awesome. It's a tie, and hopefully we decide to go and solve our problems more peacefully. In the situation where I swerve and you go straight, that's 2 happiness points for you. You look totally awesome. 0 happiness points for me. I look like a chicken. That situation is reversed in the world where I go straight and you swerve. That's 2 happiness points for me and 0 happiness points for you. I look awesome and you look like a chicken. And remember, there's the situation where we both go straight, and that's the -1, -1. So this is our game of chicken, just like we drew it up last week. My question is, which of these outcomes, there are 4 outcomes, there are 4 strategy profiles, right? Straight, 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 swerve, swerve, straight, swerve, swerve. The 4 elements of the Cartesian product. There are 4 strategy profiles. Which of them, if any, seem like a reasonable prediction to you? Pause the video. But which, if any, it could be one of them, two of them, three of them, all four of them, or in fact, it could be none of them. Which of these seems like a good prediction to you? Welcome back to the none of you that paused the video. Well, let's think about it. Let's talk through that logic I had alluded to before. So let's just arbitrarily start from one of the strategy profiles and check to see if it's a steady state, and then you'll see that we wind up thinking our way through all four of them. So let's just start from the top left corner. Let's start from swerve, swerve. That's 1 happiness point for me and 1 happiness point for you. But remember, the strategy profile is swerve, swerve. Many of you will write down the utilities as if that's the equilibrium. That's not the equilibrium. The equilibrium is the strategy profile. You'll see what I mean once we get to a formal definition. So if we're here at swerve, swerve, what I'm going to say is I'm going to think this through holding you fixed, right? So I'm thinking my way through as the row player. I'm player one. I'm going to say to myself, well, imagine that I knew that we were in the swerve column. Imagine that I knew that we were here. Right now, I'm swerving and I'm getting 1 happiness point, right? I'm getting 1 happiness point for the swerve. But if I knew that we were going to be in this column, I have a profitable deviation, right? Because if I knew that you were going to swerve, if I'm swerving, I get 1 happiness point. But if I deviated to going straight, I would get 2 happiness points because I would go from a tie to winning. I would be awesome and you would be a chicken, right? If I had my druthers, if I knew that we were in the swerve column, holding you fixed. That's what I mean. When I say we're in the swerve column, that means holding your decisions fixed. Do I have a profitable deviation? And the answer from swerve, swerve is yes, I do. What about you? You're column player. So let's just think this through, holding me fixed. So imagine that you're saying to yourself, well, assume that row player is swerving. Just think about that. Just hold that thought for a second. If we knew that row player was going to swerve, if you knew that I was going to swerve, right now you're getting 1 happiness point for the swerve, swerve outcome. But if you deviated, you would go from 1 happiness point to 2. You would go from tying to winning. If you knew I was going to swerve, you wouldn't swerve. If you knew I was going to swerve, you'd go straight. So you'll notice that I have a profitable deviation. I could go from 1 to 2. And you have a profitable deviation. You can go from 1 to 2. Right? We both have a profitable deviation. Because at least one of us has a profitable deviation, and in fact, in this case, we both do, but 1 is enough. Because of that, swerve, swerve is not a Nash equilibrium. We can rule it out. We can just rule that out. It doesn't satisfy the necessary condition of a steady state. If that was the outcome out in the wild, if you thought that that was the outcome out in the wild, I would say to you, well, why doesn't somebody change their mind? That just doesn't seem like a reasonable way to proceed. If we're giving players the agency to make choices in this strategically embedded environment, then it's reasonable to say, well, if we find ourselves in a state of affairs where somebody else could profitably deviate, then they would do so. So we ruled out one of the profiles. Let's check another. So just to keep things spicy, let's go to the straight one, right? This is the one where we're in a fiery car crash, or we've landed in some ditch off of a cliff. So -1 happiness points for me, -1 happiness points for you. Okay? So let's think this through from role player's perspective to begin with. So if I knew that we were in this column, right? If I knew that you were going to go straight, I could either continue to go straight as I am and get -1 happiness points and die, or I could deviate and just lose. I could just be a chicken, which sucks, but it's better than being burned, right? Some chickens are burned, but I would rather be up here. If you told me that for sure you were going to go straight, then I would swerve. I wouldn't go straight. I wouldn't go straight, right? I have a profitable deviation. I can go from -1 up to 0. Notice also that the same goes for you here. So here we are. You're getting -1 happiness points. And if you knew that we were in the bottom row, if you knew that I was going straight for sure, right, you could either continue to go straight and die in a fiery car crash, which is worth -1 happiness points, or you could just be a loser.
Loser.
Call Beck. I'm a loser, baby, so why don't you kill me? Well, that was what would happen here. Now you're just a loser. It's Beck was wrong about the whole thing. So we both have a profitable deviation from swerve, swerve. And because at least one of us does, remember, it only takes one. A lot of these games have a symmetric flavor, these introductory games, and so there's going to be a whole lot of, if there's one, then there's both. But that won't necessarily be the case. Sometimes it'll just be one person wants to deviate, and one person wanting to deviate is enough. So we can rule out straight. We've already ruled out two possibilities. We've ruled out straight, the fiery car crash. That's pretty good. And we've ruled out swerve, right? So we've already gotten rid of two of the profiles. We don't have to worry about those. Our prediction will not include those. Okay? Now, if you saw those out in the wild, then you'd have to say to yourself, well, maybe this isn't an appropriate model. Maybe this model is wrong in a sense, although I don't know what that means. Or maybe we need to update our model. Maybe we need to add things to our Mr. Potato Head doll in order to make it work. But as of right now, we're just thinking about the act of predicting in the abstract. I know it's hard to believe. All right, so let's consider one of the other outcomes. So suppose that I am swerving and you're going straight. So suppose we're in the situation where I get 0 happiness points and you get 2. Okay? We're at the swerve straight. Now let's think this through. I'm role player. I'm saying, well, suppose that I knew that I was in this column. If I knew that you were going straight for sure, I could either do what I'm doing right now and swerve and get 0 happiness points. I'm a chicken. Or I could go straight. Maybe I could profitably deviate by going straight. Except I would die. Psh, nope. Not a profitable deviation. So even though I lost, even though I got a bad outcome, I have to take you into account. And if I knew that you were going straight, I would choose to swerve. I wouldn't go straight. I just wouldn't go straight. What about you? You're column player. So right now we're up at the top right. We're at swerve straight. And you're getting 2 happiness points. And suppose that you were thinking about what would happen if you knew that I was in the top row, if you knew that I was swerving for sure. Well, if you knew that I was swerving, you could either continue to go straight and win and get 2 happiness points, or you could deviate to swerving and just end up in a tie and get 1 happiness point. You don't have a profitable deviation either. You got what's called your first best outcome. It's the single unique best thing. Nobody ever wants to deviate from their first best outcome. So notice, this is different now. Right? So from here, I don't want to deviate because I would die, and you don't want to deviate because you would tie. That's worse for both of us. This is a pure strategy Nash equilibrium. This is a Nash equilibrium. This is your first Nash equilibrium. Swerve straight is a Nash equilibrium because neither of us has an incentive to deviate. Neither of us has an incentive to deviate. I would go from 0 to -1, and you would go from 2 to 1. That's a steady state. If we found ourselves there, I wouldn't deviate, and you wouldn't deviate. If that was happening out in the wild, then we would stay there. It's like a sinkhole. It's sort of like a gravity point. Just for completeness sake, let's observe that the same thing happens when we're in the situation where I win and you lose, if we're at straight swerve. So let's just think this through again for completeness and repetition's sake. So right now I'm getting 2 happiness points and you're getting 0. If I knew that you were swerving, I could continue to go straight and get those 2 happiness points. I can continue to enjoy my first best outcome. Or I could deviate and tie. I don't want to do that. I don't want to go from 2 to 1. I want to stay at 2. I'm not going to deviate. I'm going to stay right where I am. And you, well, you're thinking through, well, if I knew that Rob was going to go straight, if I knew that we were in this bottom row, then I could either continue to swerve and get 0 happiness points or go straight and end up with -1 happiness points. I don't want that. That's a steady state too. So we wind up with 2 pure strategy Nash equilibria. I'm going to keep saying pure strategy Nash equilibria, and that's just going to be Nash equilibria today, but you'll see that there's something additional that we'll be talking about next week. So right now we've got 2 pure strategy Nash equilibria, the one where I win and you lose, and the one where you win and I lose. So our prediction is somewhat indeterminate. We don't have a unique prediction. If you asked me what to predict, I would say something of the form, somebody's going to win and somebody's going to lose. I can't tell you who, but somebody's going to go straight and somebody's going to swerve, and that's it. So the thing that I could tell you, the qualitative punchline of this analysis, the prediction that we make from chicken is that there's a winner and a loser. It's not going to be the case in the analysis of this game that they're both going to back down or that they're both going to keep going forward. Eventually, the equilibrium is somebody swerves. So now that we've seen this example, let's talk about a formal definition of Nash equilibrium. In order for me to do that, I'm going to have to introduce a slight abusive notation that's very common in game theory. It's in your textbook. You're going to see it everywhere. Just suppose that we've got a set of players, capital N. We could just number them 1 through N. If it's 2 players like we just had, then it's just player 1, player 2, but it could be 370 million people. Who knows? Okay, so we've got these 2 players or N players. It's the same idea. And remember, each one of these players has a strategy set, capital A sub I. Those are the available actions. In chicken, the 2 players have the same action set, straight or swerve. And remember, as part of our game, we also get to take as given the utility function. So the story that I told you, the whole matrix that we talked our way through at the start of the block, that matrix we take as given too. So we walk in with a game, which is a set of players, a set of things that each player can do, and a set of utilities for each player over the combinations of choices. And remember that a strategy profile is just a set of choices, one for every player. Right? So it's like A sub 1, A sub 2, A sub 3, ... A sub n. So if I say A, little a, all that is a set of choices, one for every player. Little a player 1, little a player 2, little a player 3, and so on. Now, in order for me to be able to write down this idea that we're talking about, this no player has an incentive to unilaterally deviate, I need to talk about how to abuse notation a little bit on this strategy profile. So whenever I say A sub minus I, what that is the strategy profile A with the ith choice removed, right? So if I say A sub minus 1, that means conceptually it's the strategy profile with player 1 not in there. So that's A sub 2, A sub 3, A sub 4, ... A sub n. If it was A sub minus 2, it would be A sub 1, A sub 3, A sub 4, ... A sub n. So whatever is the minus thing, we're just taking it out of there. And then the abuse of notation is it allows me to write out this ordered list of choices, A, and then if I want to call particular attention to player I's choice, then I can write that as A sub I, A sub minus I. So if it's player 1, the strategy profile could be written A sub 1, A sub minus 1, which just means call particular attention to player 1's choice. And the same for player 2, A sub 2, A sub minus 2, and so on. You'll see why I'm going to do this here in just a second. So we say that a strategy profile A, which is A sub 1, A sub 2, A sub 3, ... A sub n, which could just be like straight, or straight swerve, or swerve straight. It could be simple. It could be just two players. So we say that a strategy profile, call it A, is a pure strategy Nash equilibrium. And now we have to encode the idea that no player wants to deviate. So we're going to say that for every player I in N, for all I in N, for every player, for every individual, for adolescent A and adolescent B, it has to be the case that the utility that they get for playing A as specified in the strategy profile against everybody else. So if I say A sub I, A sub minus I, that means the utility that player I gets from the current strategy profile where they're playing A sub I and everybody else is playing their respective A, right? So if it's player 1, they're thinking about if player 1's utility for choosing A sub 1 against A sub minus 1, holding everybody else fixed. That's what I'm saying. Hold everybody else fixed. That utility has to be greater than or equal to the utility that player would obtain for deviating to any other available action. So that utility must be greater than or equal to U sub I, player I's utility, for deviating to some A sub I prime against the same A sub minus I. So you'll notice that it's the same A sub minus I. I wonder where I'm going to aim it. So it's the same A sub minus I, holding everybody else fixed, treating everybody else as given. Imagine I'm in this one row for sure. Imagine I'm in this one column for sure. That's what I mean here is hold the A sub minus I fixed. Hold the other player or players fixed. And the question is, do I do better for playing my A against that, or do I want to deviate to AI prime? And if nobody wants to deviate, if everybody's happier here than they are for deviating, if every player satisfies this condition, it's a pure strategy Nash equilibrium. So let's just take that over to the game of chicken again, and let's just get some practice. Let's just think about swerve, which isn't a Nash equilibrium, right? So swerve, I'm getting 1 happiness point and you're getting 1 happiness point. Let's think this through from my perspective. So if I equals 1, if player I is player 1 for now, then that means that A sub minus I is player 2's choice. So the question is, holding you fixed, holding A sub minus I at swerve, holding you fixed, do I want to deviate from my current A sub I to A sub I prime? Do I want to go from A sub I to A sub I prime? And the answer is yes. And the same for you. If I is 2, if we're focusing on player 2, then now a sub minus I is player 1. And so the question becomes, do you want to deviate? Do you do better for playing a sub 2, which is swerve, or for a sub prime 2, which is straight? That's one of the possible deviations. In fact, it's the only possible deviation in a 2x2 game. And the answer is yes, you want to deviate. So that's not a pure strategy Nash equilibrium, because there exists a player, either of us, such that they would benefit from deviating, holding everybody else fixed, a sub minus I. So conversely, for these two equilibria, notice that holding you fixed, I don't want to deviate, and holding me fixed, you don't want to deviate, right? So you might have to stare, you might have to light a candle and stare at this game of chicken for a while so that the notation from that definition of pure strategy, Nash equilibrium, makes sense to you in the context of the picture. But that's it. It really is holding everybody else fixed. Does anybody want to deviate? And if not, then we are at a steady state, which is a necessary condition, but not sufficient to be a prediction. Why not sufficient? Because there might be multiple equilibria. So now you've seen Nash equilibrium, and it's just a matter of us figuring out a more efficient way to compute it and plowing our way through some more examples. We'll do 2 games with a different approach over in the B block. I'm looking forward to bloviating over there for you. So here in the B block, I want to talk about Nash equilibrium as the intersection of best response correspondences. Oh man, you're going to crush so many dinner parties. You're going to crush them so hard. So the thing is, if you're checking all of the different strategy profiles and whether there's proper deviations, that winds up being an awful lot of computation. And even though the concept of a steady state makes an awful lot of sense, it just isn't super handy to compute equilibria all the time. And it turns out that you can think about Nash equilibria with a different substantive motivation that winds up being equivalent, which is nice. It's neat to have 2 different stories that are actually the same thing. So in order to animate this notion of best response, let's talk about the coordination game. You remember, the idea here is I'm a driver, you're a driver, we're 2 drivers. And remember, the basic idea of coordination is we either want to both drive on the left side of the road, that's probably over there, or we both want to drive on the right side of the road. We don't want to find ourselves like here where I'm on the right and you're on the left, or here where you're on the right and I'm on the left. We don't want that, because then we're in a fiery car crash. So 1 happiness point apiece if it's left, left, or right, right. 0 happiness points apiece if it's left, right, or right, left. So here's how we're going to animate things this time. So what we're going to do is I'm just going to go through every column, and I'm going to think it through from role player's perspective. And for every column, I'm going to say, what is the best thing that role player could do in that column? And I'm just going to mark it. You know, the equivalence to the steady state thing will be pretty obvious, but the algorithm I'm using, if you just focus on how I'm talking my way through this, it's actually a very different story. So here's what we're going to do. I'm going to say, suppose that I knew that you were on the left side of the road. Suppose I knew that you were driving on the left side of the road. Now I could either drive on the left and get 1 happiness point, or I could drive on the right and get 0. I would rather drive on the left. So I'm just going to put a star underneath that. That's my personal notation that 1 is the best you could do in that column. But please remember that your best choice, that means the best choice is left. Not that the best number is 1. The numbers are arbitrary. The best choice is left. Okay? If I knew that you were driving left, I would also drive left, which would get me 1 happiness point, which is why I put a star there. There's no way I aimed any of that correctly, and Editor Rob is having a conniption right now. Who cares? I'm the babyface. Now let's move over to the column where you're driving on the right side of the road. So if you're driving on the right side of the road, then I could either drive on the left side of the road and get 0 happiness points, or I could drive on the right and get 1. I would rather drive on the right side of the road, so I'll put a star underneath that 1 here. And remember, that means that my best response to right is right. Now let's think about you, your column player. Well, if you knew that I was in the left row, if you knew we were in the top row, where I was driving on the left side of the road, you could either drive on the left side of the road and get 1 happiness point, or drive on the right side of the road and get 0. You would rather drive on the left side of the road, so I'll put a star underneath your 1 there. And if you knew that I was in the bottom row, if you knew I was driving on the right, you could either drive on the left and get 0 happiness points, or drive on the right and get 1. You would rather drive on the right. I'm going to put a star underneath your 1 down here for right, right. Now notice that 2 of the strategy profiles, namely left, left, and right, right, have 2 stars. 1 star for every player. And the other two profiles, left, right, and right, left, have 0 stars. It turns out that if a profile is the best response for every player, right? So if there's a star for every player, then that's a pure strategy Nash equilibrium too. So if I were you, which I'm so sorry, so if I were you, I would try to do a steady state analysis of this coordination game just to confirm that the pure strategy Nash equilibria are left, left, and right, right. So when I talk about best response, what a best response correspondence does is it reads in an A sub minus I. So if I've got capital B sub I, that's player I's best response. So player I's best response to everybody else's choice A sub minus I, which in this case is just what the other player does, the one other player. So it reads in what everybody else is doing, and it spits out the best or the set of best choices if there's indifference. Indifference is possible. You haven't seen a game with that just yet. I'll put one on your problem set. What B sub I of A sub minus I is the set of all choices the player one could make that maximize the utility when everybody else is playing A sub minus I. It's just a set. It's just a set. It's just a set. Look, this is just a set right here. It's just a set. It reads in what everybody else does and it spits out the best thing for you to do. That's a best response. And what I'm saying is if a strategy profile is a best response for everybody, holding everybody else fixed, then that's a Nash equilibrium too. Mutual best response. Now it's not a steady state thing. Now it's not like people are out in the wild. Now it's not like people are just kind of making their choice and deciding whether to deviate. Now it's like I'm playing this game of coordination with you, right? And I'm thinking through what you're doing and you're thinking through what I'm doing and we're best responding to one another. It's a much like more personal account, right? You'll notice that there are two pure strategy Nash equilibria in this game, left, left, and right, right. You'll notice that we play only one of those equilibria here in the United States. In the United States, if you are a driver and you're driving, it is expected that you will be playing the right, right equilibrium. You will be driving on the right side of the road. You will be driving on the right side of the road. The right side of the road, right? You'll notice that there are other countries, say the United Kingdom, where drivers are expected to play the left-left equilibrium. People there drive on the left side of the road. So my question to you is, why do you drive on the right side of the road? You can pause the video if you need to. Why do you drive on the right side of the road? What's so special about the right side of the road? I just told you in the United Kingdom, they play the left-left equilibrium. Every day, if you drive, every day that you drive on the right side of the road, I'm assuming, unless it's one of those experiences that I discussed last week where people are driving in the state of nature that is Green Street. When you're driving, you drive on the right side of the road, and I don't know why. Do you? I want you to think about that for a second. Have you thought about it for a second? Because it's important. You need to reflect. You need to contemplate on why you drive on the right side of the road, given that it's just as of a Nash equilibrium. It's no more equilibrium-y for us to drive on the right than it is for us to drive on the left. People in the United Kingdom seem perfectly happy. Why do we drive on the right? Pause that video. Reflect for 90 seconds. 90 seconds at least. 90 seconds at least. 90 seconds. Why do you drive on the right side of the road? Why do you personally drive on the right side of the road? Welcome back to all of you drivers. The reason that you drive on the right side of the road is it's the law. That's the law. You have to drive on the right side of the road because that's the law. The law says you have to drive on the right side of the road. That's why you drive on the right side. That's the law. The law says you have to drive on the right side of the road. Don't you feel like you're getting your money's worth right now? You needed me to tell you that the law says that you drive on the right side of the road? You don't need other classes. I mean, this is the best class you could take because I am the uniquely insightful professor that can tell you that you drive on the right side of the road in the United States because it's the law. You and millions of other people, when you drive in the United States, you drive on the right side of the road. Every minute of every hour of every day, millions of people are driving on the right side of the road because it's the law. And I'm the one that told you that, and I feel pretty good about it. Now tell me something. Why is it the law? Why do we need a law for that? Why do we need a law to tell us to drive on the right side of the road? It's a pure strategy Nash equilibrium for us to both drive on the right side of the road. Why do we need a law to tell us to drive on the right side of the road when, in the absence of anything else, We agree that that's an equilibrium thing for us to do. Why do we need a law for that? Why do we need a law? Why do we need a law to tell us to drive on the right side of the road? Because there's two equilibria. Right? Right is a Nash equilibrium, but so too is left. So what happens is the fact that there are multiple equilibria, the fact that this game has two equilibria, which are interchangeable. One isn't better than the other. There's not a Pareto improvement argument. There's no argument to make other than the fact that we want to get where we're going. But there's ambiguity because we don't know which way to get to where we're going. We don't know if we're playing the right one or the left one. If we woke up both feeling like we're going to play Nash equilibria today, we both are looking for Nash equilibria because it's in our best interest in the coordination game. We're both saying to ourselves, I want 1 happiness point for Culver's rather than 0 happiness points for a fiery car crash. Hypothetically on the Culver's. Very hypothetically, okay? We both want the happiness point, and we don't care which. We don't care how we get there, but if I woke up thinking we're playing the right equilibrium, and you woke up thinking we're playing the left equilibrium, then even though we've thought this through and put stars underneath the numbers, and maybe we thought about steady states and we invoked John Nash and Augustine Cournot, fiery car crash. Even though we're both doing equilibrium-y things, we don't know which equilibrium is the one to play. We need the state to tell us which coordination solution is the solution. We need to help coordinate on our coordination. The state helps us by arbitrarily saying, drive on the right side of the road or else. The state solves coordination problems, among other things. But a minimal thing that the state has to do is tell us which of these arbitrary, we don't give a shit equilibrium. We really don't give a shit. We just need somebody to say, okay, it's right day today. And you wouldn't want to change every day, so it's right day every day. And we make a law. We institutionalize that. We institutionalize it because there's multiple equilibria. It didn't always used to be that way, and you can understand why if you think about not drivers, but rather people walking around campus. So suppose that you're walking around campus. Suppose that we're walking toward one another on the South Quad. So if we're walking toward one another on the sidewalk, we both just want to get to where we're going. You'll notice that there isn't a law that tells us to walk on the right side of the sidewalk, but there does exist a norm. Most people will move to the right. Why? It's interesting when you think about it, right? So we kind of play the right equilibrium when we're walking, but we don't need the law for that. We just do it on a norm. And back when cars were a little slower, and back when roads weren't quite so ditchy, and back when you didn't have to have perfect conditions, back when driving was a little bit more like walking, a norm governed that too. And as cars got faster and heavier and more deadly, we wound up needing some help to solve the coordination problem by letting us know which of these multiple equilibria to play. And I'm telling you, that's what countries do. Among other things, they choose from multiple equilibria. Now, is that it? Is that all that states do? It seems to me that if you read the newspaper, states are doing an awful lot more than just saying drive on the right side of the road. So let's think about another motivation for the state. Let's think about the prisoner's dilemma. So remember, I'm a suspect, you're a suspect. We are two suspects. We've been put into separate interrogation chambers by some really smart sounding people, some detectives that seems like they might be pretty good at getting information out of us. So they put us in the room and they say, well, if you tattle and the other person doesn't tattle, then you get to go free. If neither of you tattles, we got you for a misdemeanor. If both of you tattle, then we'll just put you both in jail. And if you get tattled on and you don't say anything, we'll put you in jail for the rest of your life. So in other words, I can stay silent or I can tattle. And you can stay silent or you can tattle. Silent, we both go to jail just for a misdemeanor, maybe we pay a fine, 3 happiness points apiece. Tattle, silent, now I'm at home and you're in jail for the rest of your life, 4 for me, 1 for you. Same thing in reverse, if I stay silent and you tattle, that's 1 happiness point for me and 4 for you. And finally, if we both tattle, that's 2 happiness points apiece. So let's put stars in this game. Let's do the best response correspondence thing as practice. So suppose that I knew that you were going to stay silent. I could either stay silent and get 3 happiness points or tattle and get 4. I'd rather tattle. I'll put a star underneath that 4 to let me know that my best response to you staying silent is to tattle. Similarly, if I knew that you were going to tattle, I could either stay silent and get 1 happiness point for being in jail for the rest of my life, or I could tattle 2 and we could be buddies in prison potentially, and I get 2 happiness points. I would rather tattle. I will put a star underneath that 2. Think about this. My best response to you staying silent is to tattle. And my best response to you tattling is to tattle. What about you? You're column player. So if you knew that I was going to stay silent, you could either stay silent and get 3 happiness points, or you could tattle and get 4. You'd rather tattle. I'll put a star underneath that 4. Similarly, if you knew that I was going to tattle, you could either stay silent and get 1 happiness point for being in jail for the rest of your life, or 2 for being in jail for a long amount of time with potentially your buddy Rob. You'd rather get the 2 happiness points, so I'll put a star underneath that 2. So your best response to silent is tattle. Your best response to tattle is tattle, and the same for me. Well, are there any strategy profiles that have 2 stars? Yes. Tattle, tattle. The unique, pure strategy, Nash equilibrium of the prisoner's dilemma is for us to both tattle. You might just have written that down. And I want you to close your notebook. And I want you to just pause. In this situation, the shepherds, the tragedy of the commons, public good provision, common pool resources, not overexploiting, arms races, not getting too many arms. There's a lot of things you can model as a prisoner's dilemma. And in all of them, there's a sad ending to the story, a repugnant ending to the story where both of these players, because of the arrangement that they find themselves in, be it something imposed like by detectives or something that happens organically like with the shepherds, no matter what the case is, the tragic ending to this story is that everybody tattles. Everybody does the greedy thing. Everybody does the nasty thing in the prisoner's dilemma. Now, why is that so repugnant? Because there's a Pareto improvement on the board. Tattle tattle is Pareto dominated by silent silent. 3-3 is strictly better for both of us than 2-2. Paying a fine for a misdemeanor is strictly better for both of us than going to jail. And yet, because of the collective action problem, because of the individual level incentives, because of what's encoded in this stupid matrix, because of what's underneath the hood, we both do this nasty thing to one another. Let's think about this in the utility imputation space, just to make sure that you're internalizing it all the way. Now remember, in a utility imputation space, for the purposes of the prisoner's dilemma, we've got the row player's utility here, we've got the column player's utility here. Remember, we've got like 3-3, 2-2, we've got way over, we've got 4-1 and 1-4. And remember, tattle tattle is Pareto dominated by silent silent. And yet, it is the unique prediction of the prisoner's dilemma. Now, because there's a unique Nash equilibrium, my justification for the state has no bite. Because I told you what the state does is it chooses out of multiple equilibria so that we know which equilibrium is the equilibrium that we're playing. But in the prisoner's dilemma, there's only one equilibrium, so we don't need the state. Is that true? Suddenly, the state does something very different. Instead of like benevolently choosing an equilibrium for us, instead of saying, well, you guys don't know if you want to drive on the left or on the right, so we'll just say we drive on the right so that everybody knows. That sounds like a pretty happy, nice state. Here what the state is saying, listen, your incentives are off. And in order for me to get you to behave well, I'm going to have to shift your incentives. I'm going to have to punish you if you do the wrong thing, or I'm going to have to offer you some positive incentives for doing the right thing. Regardless, I'm talking about shifting your incentives away from the prisoner's dilemma to something else. Now notice that that solution may be costly. And so we might wind up with something that's a Pareto improvement over tattle tattle, but still isn't quite as good as silent silent would have been. Regardless, if we're living in a prisoner's dilemma world, we need a very different state than if we're living in a coordination game world. And of course, we're living in both worlds, and so the state has to serve many functions. That function might be something that happens in the context of multiple equilibria, like in the coordination game, or it might be something that happens in the context of a single awful equilibrium, like in the prisoner's dilemma. Regardless, what happens here is we're both just making individual level choices. We're both just coming up with our own best responses. We're just trying to do atomistically what is best for us. There doesn't necessarily have to be any ill intent. We're just trying to do what seems best for us, conditional on what everybody else is doing. And in one situation, we kind of need a little gentle nudge just to drive on the correct side of the road. And norms would have been just fine there. But in the other world, it's like, oh man, we need the state to just kind of change everything for us so that we don't find ourselves in this awful situation. From 2 stupid matrices and a bunch of stars that we drew in it, there's a lot going on underneath the hood if you just let it. You just gotta stare at the screen. You gotta get the osmosis. You know, it might be, here, if you need to stare at the screen, I'm gonna put these 2 games here, and you might not want to stare at the screen when my ugly face is here. So, how'd that go for you? Did the osmosis happen? Did you get the magic eye effect? Did you see it? Yeah, you saw it. I know you saw it. That's the good stuff, right? So I got some more good stuff to show you over in the C block in terms of campaigns. Looking forward to it. See you there. So here in the C block, I want to talk about that campaign from last week. So you'll remember that the basic idea is that there's a policy space. So we have this policy space, and just to animate things, we'll again put 5 voters in this policy space. There's a far left voter, a center left voter, a center voter, a center right voter, and a right voter. 1, 2, 3, 4, 5. They all have ideal points in this space, and they all have absolute value utilities, just like before. Isn't that nice? I mean, as you get more comfort with this, it's just a matter of like, oh, you remember the story. Let's just pick up where we were in the story before. It's just the story is really complicated now. Except it isn't. Look how fast you've gotten. And remember, the basic idea is that there's majority rule and the candidates just want to win. So if they win, they get 1 happiness point. If they tie, they get a half a happiness point. And if they lose, they get 0 happiness points. They're just office motivated. They just want to be elected to office and have a Wikipedia page. So from a steady state perspective, let's consider the following situation just anecdotally. So suppose that, without any loss of generality, suppose that candidate 1 was pretty far to the left, and the candidate 2 was closer to the middle, but still to the left. Is this a steady state? So A sub 1 strictly less than A sub 2, strictly less than X hat 3, right? So in other words, the first platform is to the left of the second platform, which in turn is to the left of the median voter. Well, in this current situation, candidate 2 wins. Candidate 2 is getting 1 happiness point. Candidate 2 is getting 1 happiness point because they get voters 2 through 5, as I've drawn this, and candidate 1 only gets voter 1. So candidate 2 has no incentive to deviate because they're getting 1 happiness point, which is as well as they can do. They don't want to deviate because there's no strictly better outcome. There's no strictly better outcome than winning. They are perfectly happy. However, it's worth thinking through whether or not candidate 1 has any incentive to deviate. Is there some policy that they could choose that would get them a better outcome than losing? Do they wish that they could have chosen some other strategy? Pause the video and think about it. And if so, which policy or policies would they choose? Pause the video. Well, let's think about it. Let's just say that candidate 2 is right here. So long as candidate 1 is strictly to the left of this, so long as their platform is strictly more leftist than candidate 2, they will lose. They could deviate and have exactly the same policy platform as voter 2, as candidate 2, and they would wind up with a tie. That's strictly better. They wish they could deviate. They would go from 0 happiness points for losing to a half a happiness point for tying. What's more, if they went even just a little bit to the right of candidate 2's ideal point, if they just a little bit, they would win. They would win. So candidate 1 wants to deviate to somewhere. It could be exactly to where candidate 2 is, or somewhere to the right. So they could go too far though, right? So if candidate 1 goes too far to the right, if they go further right than candidate 2 is left, then eventually they're further from the median again, and then they would lose. So given where candidate 2 is, there's 2 tie points, and then there's this win set. They could deviate and win. So it's not a Nash equilibrium for candidate 1 to be strictly to the left of candidate 2 if they're both left of the median. The same works for candidate 2 strictly to the left of candidate 1. And the same goes for both of them on the right side of the spectrum. So right now we have said there does not exist a pure strategy Nash equilibrium where both candidates are on the same side of the median and one is further away from the median than the other. We've ruled that out. We've completely ruled that out. You could just generalize that logic. You could put two to the left of one and they're both to the left. You could put them both on the right. The same logic applies. Work it through if you need to. Work it through. Come to office hours if you need to and we can work it through. But there does not exist a Nash equilibrium where they're both on the same side and one is further than the other. What about a Nash equilibrium where they're both on the same side and they have the exact same platform? What if they were both at the same exact platform on the left side? Now they're both getting half a happiness point, right? They're both getting one half of a happiness point for the tie that they get for being the same distance from the median. Does anybody want to deviate? Yes, if you move just a little bit closer to the median than where you were, you go from tying to winning. So if we were both to the left of the median, I would just move a little bit to the right and get everybody on the right side. I would win. It would be great if I could win. I would win. You could win. If we were both on the same platform and it wasn't the median, then if you deviate, you can animate it. You could just switch to the median's ideal point and you're doing fine. So there doesn't exist a pure strategy Nash equilibrium where we're both on the same side and we have the same exact policy there. Okay, so that's like all of we're on the same sides. So let's say that neither of us at the median, but we're on different sides. If one of us is further from the median than the other, then that means there's a winner and a loser. So whichever of us is further, so let's say that candidate 1 is here and candidate 2 is here. Candidate 2 is closer to the median. Candidate 2 wins, candidate 1 loses. Candidate 1 could deviate to, for example, the median's ideal point and go from losing to winning. So there does not exist a pure strategy Nash equilibrium where they're on opposite sides and one is further from the median than the other, right? Because you want to deviate. Well, what if we're away from the median, but we're the same exact distance from the median? What if we just happen to be like mirror images of one another, right? However far we happen to be, we're the same distance from the median. It could be we're both really close to the median. It could be we're both really far from the median. But what if we're both the same distance from the median? Well, if we're both the same distance from the median, it's a tie, right? So it's a tie. Is there a profitable deviation for either candidate? Yes, if either of us deviates to something closer to the middle, then we win for sure instead of tying. If you deviated to the median ideal point or something closer to the median ideal point than where you were, then you go from tying to winning. Therefore, there does not exist a pure strategy Nash equilibrium where the two candidates are on opposite sides of the median and they're the same distance. Now suppose that I was on one side of the spectrum and you were right at the median. We haven't thought about that just yet. So if I'm at the right side of the spectrum, or the left, if I'm away from the median and you're right at the median, then you're winning and I'm losing. You don't have a profitable deviation because you're winning, you're happy. But if I deviated to exactly the median ideal point, if I deviate to anything else, I still lose because you're at the median ideal point. You have the median completely happy. All right, so if I deviate to anything that isn't the median ideal point, I still lose. But if I deviate to the median ideal point, I tie. I go from losing to tying. Therefore, I have a profitable deviation. There does not exist a pure strategy Nash equilibrium where one of us is at the ideal point of the median voter and one of us is not. Because the one that isn't has a profitable deviation. So we have ruled out an awful lot of things. Same side, one further, same side, the same. Opposite sides, one further, opposite sides, the same. That seems to be everything, right? Is that everything? That seems to be everything. What'd you say? Sorry, I'm getting old. One more time? I can't hear you through your mask. Oh, what if they're both at the median? Oh. I hadn't thought about that. So suppose that we're both at the median ideal point. Candidate 1 is at the median ideal point. Candidate 2 is at the median ideal point. And therefore, we both have a happiness point. It's just impossible to say. Therefore, we both have a half a happiness point. Therefore, we both have a half a happiness point. It's so hard. You try it.
Therefore, we both have a half a happiness point.
Thank you. So we both have a half a happiness point. And if either of us deviated, if you deviate to the left, then you go from tying to losing. That's not good. And if you deviate to the right, then you go from tying to losing. That's not good. Neither player has an incentive to deviate. The unique pure strategy Nash equilibrium of this campaign model is for us both to have our platforms exactly at the median voter's ideal point. It can't be that we're both away from it. It can't be that we're on different sides of it. It can't be that one of us is there and the other isn't. The unique prediction of this model is that we're both at the median. The blues go to the median, the reds go to the median. This has a name. It's called the median voter theorem. The unique equilibrium of this simple campaign model, which we agree looks like a campaign model, the unique equilibrium is for us both to go to the middle. Now, have you read the news? Because I got news for you. That isn't what happens. That isn't what happens in campaigns. It used to happen a little bit more than it does. It used to be like you had to kind of win the primary. Notice that we haven't talked about primaries. You used to have to kind of win the primary by going far in the respective direction of your party. And then once you won the primary, you would immediately try to get back to the middle. There was an old SNL sketch where Dana Carvey played George H.W. Bush. And he's doing like, you got to shimmy back to the middle. You got to slide back to the middle. You got to slide back to the middle. And that's less the case these days because it like turnout matters, whipping up your base enough matters. There's a couple other things that matter. There's a lot of other things that matter. I'm not an expert in this. But isn't it provocative that your first game theoretic analysis of a campaign, where everything seems pretty plausible, there's a lot of richness here, we've talked our way through a lot of interesting possibilities, the unique prediction is for something that doesn't happen all that much. Convergence, policy convergence. The two parties will announce the same platform. The two candidates will announce the same platform. Now, one thing that's fun about this is then you think, well, what thing or two things would you add to the model to support separate platforms? What could you do to make it a Nash equilibrium for us to be on different ends of the spectrum? That's what the whole enterprise is. You kind of start from this striking result that we're at the median voter, and next thing you know, you find yourself tempted to try to break it. You want to break the result because breaking the result might make it more realistic. And then you have to think through, what are the substantive features of interest for a campaign that might create policy divergence, and how would I encode them? And that's why professors mumble to themselves at whiteboards. That's why we're all so grumpy. That's why we have to go to conferences and try things on one another, is that we have no idea what the substantive features are to help generate more realistic looking predictions, and we sure as hell don't know how to encode them. We have to help one another figure that out by arguing. And that's the whole point. So this median voter theorem, that's a pretty big deal, right? Because it doesn't work. It just doesn't work. Much like the calculus of voting, people vote. Hundreds of millions of people vote, and yet PB minus C lets you think, whoa, what would I have to do to this model to make that work? Similarly here, what would you have to do to this model to make it work? I hope you'll reflect on that. If you're interested in American politics, think to yourself, what are the substantive features that would change this model to something with a more realistic prediction? And how would you encode them? That's a good place to stop. I'm tempted to talk through the median voter theorem from a best response standpoint, but I think we'll just talk about that on your problem set instead. And you're like, oh gee, thanks, fat man. You are very welcome. But I think that you'll see that thinking through this whole analysis from the best response standpoint introduces some technical wrinkles that also are of substantive interest. But in the meantime, before we talk about that, I really do hope that this will be a reason for you to stop and reflect. Go back and look at some campaigns if you need to. Check the historical record. Figure out what are the things that cause divergence. And if you know, email me. I want to know too. But that's the whole fun of it, is then you'll have a way to show me. You could doodle something. You could go to the whiteboard and teach me, which I can't wait for you to do. And some of you have already started to do it. But now that we have more games to play with, and now we have means for analyzing those games, you have a lot to teach me. I'm looking forward to that. So what do we talk about today? I mean, if you take a class in game theory, the word Nash has to come up, okay? And so Nash equilibrium is a foundational core concept in game theory. And what it is a mechanism that takes us from stories to endings. It takes us from sort of some data, some strategic data, the nature of some strategic interaction, sort of the rules of the game or something like that. It takes that and it says, well, if you gave me all this information, if you gave me Chicken or The Prisoner's Dilemma or some campaign, If you gave me that, then I could take you to a prediction. It might be multiple predictions, and we'll see next week it might be 0 predictions unless we augment things. And so the solution may be somewhat indeterminate. But at the very least, we begin the process of how to take a game and take it to its ending. And we saw that the necessary condition was that it's a steady state. It has to be some state of affairs where actors who are equipped with agency wouldn't deviate. If there's a situation where people deviate, we're not going to expect to see that out in the wild. We also learned that the indeterminacy of multiple equilibria creates some real substantive wrinkles about what the state is and what is the notion of order. So I'm oftentimes interested in where states come from, and some of the other classes that I teach focus on it pretty heavily, but I think it was worth talking about today. Where the state comes from, then what are the origins of order is a hard question, and it hasn't been adequately answered. And Lord knows the stupid scribble that we talked about in the B block doesn't answer it either. But I think it's interesting that our notion of Nash equilibrium immediately unlocked a really interesting, nuanced wrinkle that maybe will change how you feel when you drive. Maybe will change how you feel when you think about what the state is and what it does, or something in between. Nash equilibrium is something that you can compute very easily. The best response correspondence method is very straightforward. In the context of a 2x2 or some other finite game, it really is just a matter of drawing some stars underneath the numbers. In the context of more complicated things, we just see that the optimization conditions, the finding the best response thing, is just finding the solution to a big system of equations. And I know that sounds intimidating, but remember that you solve systems of equations in 8th grade math. And if you just think about Nash equilibrium as a big nasty way to solve a system of equations, then that's really the best response approach. It's mechanical. You could train a computer to do it. A robot can find Nash equilibrium. There's some really important work in computer science and electrical engineering about how to compute Nash equilibria efficiently. This has been award-winning work, not just in math and in game theory, but also in engineering. Because it's not easy to know how to most efficiently compute Nash equilibria. However, it is something that could be done by a computer. It is something very rote. It is something very routinized. And if you have the right algorithm, you don't need to bring any flesh and blood into this. But there's something far more human in Nash equilibrium than you may have realized. The fact that a computer can compute Nash equilibrium doesn't mean that it tells you everything you need to know. And it's with something very flesh and blood in mind that I'd like to conclude with a provocative thought. Once upon a time, you were a student and I was a professor. And you had a problem set that you wanted to turn in. Maybe you're using your 143-hour catastrophe exception, and so you can't turn it in on Canvas. And so you want to turn in your problem set, and I want to receive it. But suppose that we didn't have email or cell phones or anything. Suppose that we just woke up tomorrow on the understanding that we wanted to meet somewhere on campus at some time so that you could turn in your problem set and I could receive it. Now, because of the lack of phones and the lack of emails, all in this fable, it's just a once upon a time there was a student and professor. So because of that, there isn't any way for us to pre-communicate about where we're going to go or when. I claim that this is a massive coordination game. Okay? And let's think that through. Let's think what the rows and the columns would be in this coordination game of you turning in your problem set somewhere at some time on campus. Let's think through everywhere that you could go. Okay? So let's think through every place that we could meet on campus. We could meet in my office in David Kinley Hall. We could meet in our classroom. We could meet on the couches of the Illini Union. We could meet at the auditorium. We could meet somewhere on the 3rd floor of the computer science building. We could meet in section 172 of Memorial Stadium. We could meet somewhere deep in the middle of some field covered in shit out in the vet school. We could meet on the main floor of the undergraduate library. We could meet in the first basement of the undergraduate library. We could meet in the second basement of the undergraduate library. We could meet in one of the practice rooms in the music building. We could meet in another of the practice rooms and a third of the practice rooms. We could meet at the business school. We could meet at the Dick Butkus statue. We could meet at the alma mater statue. There's a million places we can meet on campus. From the most obscure corner of the most obscure building you can think of to something super prominent like the couches of Illini Union or the alma mater statue. And I haven't even mentioned time. Think about every time that we could choose to meet tomorrow. If we just woke up and we went somewhere to try to meet, we could meet at noon. We could meet at 1 o'clock, 2 o'clock, 3 o'clock in the afternoon, or 1 o'clock, 2 o'clock, 3 o'clock in the morning. We could meet at 3:57. in the PM. We could meet at 10:19 in the AM. We could meet at 10:22 in the PM. There's all sorts of different times that we could meet. Oh, did I just lose my light? I lost my light. That's okay. This is worth it. I'm going to lose some more of my lights, and this is totally worth it. You need to hear this one. So there's all these different times and all these places we could meet. And every time and every place is a row in a coordination game. Okay? David Kinley Hall, noon. David Kinley Hall, 1. David Kinley Hall, 1:01. Auditorium, noon. Auditorium, 1. Auditorium, 1:01, and so on. Think about every single time and place that we could meet on campus. And the idea is, if we happen to choose the same place and the same time so that you could turn in your problem set and I can receive it, then we both get 1 happiness point. And if we fail to do so, we get 0 happiness points. So in other words, if you're imagining this gigantic square that is now campus in both time and space, if you imagine this big square that is campus, then along this main diagonal, every time that we're at the same time in the same place, every single one of those is 1 happiness point apiece, and everywhere else is 0. Notice that that means that everywhere along this diagonal is a pure strategy Nash equilibrium. You could think it through steady state, or you could think it through best response. Steady state is easier. If we're at a place, we're at the same time in the same place, we don't want to deviate. We both have a happiness point for you turning in your problem set and me receiving it. And if there's a single situation where we're at a different time or place than the other person, then we both want to deviate to where the other person is. In other words, every time we're at the same place at the same time is a Nash equilibrium, and every time that we're not is not a Nash equilibrium. Nash equilibrium if and only if we're at the same place at the same time. Now, because there are so many times and so many places that we could meet, that means that there is an absolutely massive number of Nash equilibria for us to choose our way through. There are billions of Nash equilibria in this game, depending on how finely you want to slice time and space. If you want to go down to the nanosecond, or if you want to go down to the nanometer, there's more Nash equilibria than you could ever hope to count. Even if you're doing it with something a little bit more reasonable, there's a massive number of Nash equilibria. In the original coordination game that we studied, there were 2 Nash equilibria, left, and right. Here there are millions, billions, potentially even infinite. There isn't a state to tell us what to do in this context. There isn't a state to say drive on the right side of the road or else. There isn't a state to tell us which of these millions, billions, trillions, infinite equilibria to play. There's nobody to tell us what to do, and we wake up and it's time to go somewhere. So what would you do? Where would you go? And when? You get 1 shot. Where would you go and when in this situation? Think about it. I can tell you what I would do. Well, for starters, I would choose noon. Why would I choose noon? It's easy to remember. Easy to remember. Noon, 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 noon. 1 syllable, 4 letters. Noon, 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 noon. Just say it with me. Noon, noon. I don't have to say o'clock. I don't have to say AM or PM. I can just say noon. Noon is the roundest number as times go. Noon is as clean as it gets. I can remember noon so easily. Noon is the easiest single thing to remember. Why would I choose 4:22? Why would I choose 7:59? I wouldn't. I would choose noon. Why would I choose some crazy number? I wouldn't choose that. I would just choose noon. It's so easy to remember. Why are you making me remember some weird time? Noon, 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 noon. It's easy, just noon. Where would I go? I would meet you at the alma mater statue. The alma mater statue at noon. That is where I would go and when. I wouldn't go to the 3rd basement of the library. I wouldn't go to some construction site. I wouldn't go out with the cattle over at the vet school. I wouldn't be in the middle of the Moro plots getting arrested. I'd go to the alma mater statue. Why? Because it's easy to remember. Let's not make this too complicated. Out of all these equilibria, noon, alma mater statue, bing, bang, boom, done. Easy to remember. easy to stick in your head. Something wet is happening. Something flesh and blood is happening. Yeah, you could train a computer to compute those millions, trillions, billions, infinite equilibria, but they can tell you which one the people are actually going to want to play. You have to think hard about that. It's easy for me to say in this very sterile sense, and Nash equilibrium is a necessary condition for a prediction. But what does that mean? It means that if you want to get all the way to actually making a prediction, Nash can only take you so far. You have to take the sterile, the clean, the robotic, the rigorous, the game theoretic, the mathematical, and you have to inject the human into it. You have to find that one equilibrium out of many that sticks in people's head. Because even though, yeah, they could meet at some obscure part of the basketball arena at some obscure time, they're not going to remember that. They're not going to do it. It's not just going to be something that's understood between them. Now look, context can matter here. It could well be that when you thought about it, you said, I'll meet Rob at his office, and that makes total sense. But if you were meeting your friend and you didn't know where to meet on campus, I would suggest that you choose the alma mater statue or something else that's easily remembered, like the chimes or something like that, out at the Illini Union. Something that's easy to remember and that makes sense. Somewhere that's convenient, ideally, to wherever you'd like to go. We could contextualize this based on which friend you're talking about, right? So if you go get dinner with somebody at the same time every day and you needed to meet them and you didn't know when and where, meet them at your favorite dinner place at 6 or whenever it is that you young people eat. But in the absence of context, in the absence of anything else, the easiest place to remember is noon and alma mater. For human reasons, not for game theoretic reasons. Yeah, game theory said, yeah, that checks out. That's a Nash equilibrium. But it didn't tell us enough because so too were trillions of other things. They were all Nash equilibria, but we only had one chance to play this game. And we didn't have the state to tell us to drive on the right side of the road. We didn't have a norm even. We didn't have a norm like people walking on the sidewalk. We didn't even have a norm to tell us what to do. We had nothing to tell us what to do, and yet it is obvious that some of the things to do are far more reasonable than others. For purely human reasons. This notion is what the economist Thomas Schelling called a focal point. The idea that not all the equilibria are equally sticky in our brains. If we're trying to draw a border between two peoples, it's probably easiest to do so along a river or a mountain or some cultural divide that is well understood between the two of them. You wouldn't want to just draw some border arbitrarily. You'd want to respect something that can stick in their head. We've seen that go wrong in history before. If you're making any choice that matters between people that have to be reliably expected to play one equilibrium out of many, in the absence of a state and the absence of norms, you have to choose something that's going to stick in their head. That's what we call a focal point. His example was meet me someplace at some time in New York City, and he said you'd meet me at noon at Grand Central Station. Every city has a place where people would know to meet back before they had phones to text. This focal point, this one equilibrium out of many, this human thing, is one of the coolest stories that I can convey to you, even though it isn't just a game theoretic story. There's something very meta about it. It's about how we as people envision ourselves in these fables. It's about how we as individuals interpret what's going on. Yeah, the computer can compute, but it can't give you the insight. It's become a recurring theme in the class to say, yeah, there's all this math and all this abstraction, but there's also all this humanity underneath it if you let there be. And a lot of it comes down just to telling the story just the right way, which I'm sure that I just botched it, but I think I did a good enough job because it's a cool enough story. And I think that if you're going to get anything out of this class, because chances are good that you're not going to become a game theorist, but if you're going to get something out of this class, it's going to be seeing how to tell stories a particular way and then stopping and reflecting and finding the insight inside of you, finding your flesh and blood insight to help convey, to give the punchline, the human punchline, not the mathematical one, to whoever it is that you want to be talking to. These insights require nothing beyond what you already have. There's nothing I can teach you about where you would like to meet your friend on campus. You don't need me for that. You don't need game theory for that. You don't need math for that. You do need math to help to see the problem, though. You couldn't have seen the problem unless I told you the fable this way, right? You couldn't have seen this struggle of coordination. You wouldn't have known that this was a problem. It wouldn't have occurred to you that this is a complete quandary. It wouldn't have occurred to you that there's infinite possibilities and you have to choose one, feeling completely helpless. It wouldn't have occurred to you without the fable. Game theory doesn't solve problems so much as it helps us to see them. It helps us to see the invisible thing that is failure to coordinate. I'm saying all this because it's easy for you to just get bogged down in the computation. And again, we could train a computer to do that. There's award-winning computer scientists and engineers. There's award-winning game theorists that do that. But they don't have what you have. They don't have the insight. They don't have the whatever it is that's inside of you that can help create insights if you just know how to tell the story the right way. You know of problems that are game theoretic that nobody else has ever thought about. You just don't quite know the fable just yet, potentially. And so I hope that as you get more comfortable with all this machinery, and as you understand that our role in the computation is getting smaller and smaller as our computers are getting faster and faster, the sooner that you realize that our job is just to stare at the whiteboard, the sooner that you realize that what we're waiting for is the osmosis, for the flicker of insight, for the magic eye painting to just pop into place. The sooner that you see that, the better you'll feel about all this. Because it isn't just about how hard it is to climb the mountain, how all these technical details get in your way, and how it feels good to overcome them. It's also about how beautiful the vista is once you get there, and how much you would like to try to tell somebody else about it. I'm looking forward to going through this problem set with you. We'll compute plenty of Nash equilibria just like a computer does, but we'll also take the time to stop and reflect, to stop and say, what's human about this? And I hope that you'll be generous with your energy with that. There's something unique inside of you that if you can learn how to tell fables one way or another, be they game theoretic or otherwise, if you learn how to express yourself in just the right way, then maybe you can help somebody to see a problem they didn't know about and maybe work toward a solution with them, a human solution. So please, teach me everything you know. I'm looking forward to seeing you. In the meantime, thanks for watching.